All right, so here's how this was graded. Again, as always, count points, add them up, make sure I got added right, things were added right. So for problem number 1, this was worth 10 points. So the linear model for this, the rolling moment. So the difference between this and our normal model is there's 2 ailerons. So you have to put both of those in. Optionally, you could have put the thrust vectoring in here. I didn't require that because you could assume the thrust vectoring did not roll the airplane. So the points were given for this term, and this term included those. In the book, sometimes he neglects CL0, says it's small. It says 1, 2, 3 points, and then for the pitching moment. So the flap is how we do pitch control. And the points here were for the 3 terms there. Again, these were exactly like what we had before. This is the flap instead of the elevator is doing pitch control. So you need to include the thrust vectoring, the beta term, and both ailerons, because we talked about how the ailerons can cause the airplane to yaw as well as roll. So that's a total of 10 points there. Questions on that one? Again, count up, make sure I gave you the appropriate amount out of 10. And as always, if you have questions, I'm open to hearing what you have to say during office hours. Okay, so part 2, or problem 2, was the rudder deflection. So we're talking about yawing moment due to rudder. So I ask you to clearly draw positive rudder. And our definition for positive rudder is that it produces a positive side force. So that's, you should have drawn a positive rudder this way, drawn a side force this way, and then you were asked to describe this in terms of forces, which is that, and moment arms, which is this. So you needed to draw those 3 things. This was worth 15 points. So each of these were worth 3 points each. 1, 2, 3. But hang on a second, let me finish, then I'll open it up. And so then what you need to say in the description is a positive rudder gives a positive FAY with this acting aft of the CG gives you a negative pitching moment. That's the story. And it's not fiction, it's fact or physics. So maybe that's fact, physics, fact. I don't know. I just invented that. So, and then the explanation down here was worth 6 points. And a key thing that I saw people missing was talking about how the moment arm gave you the negative yawing moment. And that's really important because you could have a vertical tail in front, and I think we had a homework like that, right? So if the vertical tail were in front of the CG, the rudder would produce a positive yawing moment. All right, you had a question. If you have specific questions about things that maybe I missed, see me. Yeah. I'll be happy to look at it. It's just I don't want to spend class time looking at your particular. So that was 15 points. And then number 3 was open book. So this was worth 25 points. And again, as the exams go on or the quizzes go on throughout the semester, they become more and more weighted toward the open book part. So you needed to look up all the numbers in the appendix. But this is airplane D, right? I needed to see your conversion. So at some point you indicated you looked up the numbers. That was worth 5 points. Although I was pretty lax about that. If you got the right answer and I saw you plug in the numbers into the formula, you did okay. I didn't take off. But you had to convert IH. So that was worth 5 points. You need to show the work. And I think almost everybody did that because you've learned that I look for that. And then you have the equation from the book. That you used the right equation was 5 points. I guess that was a giveaway, right? And then plugging in the numbers was worth 5 points. And the correct answer with the correct units was worth 5 points. That should have 25, right? And I think almost everybody did really well on this because you had the book and you plugged in numbers and you knew the right formula and you calculated it. All right, so that's half the exams in the class. Well, we have final as well, right? Any questions on that last one? All right, on the board, I'm going to do an outline of what we're going to be doing next. And I think when we get into the actual derivations, I'll jump over back to the iPad or to the touchpad. So we are now jumping back to chapter 3. Chapter 3 had the steady state forces and moments. And then it has a section on the small perturbation forces and moments, which we skipped. because we wanted to solve the trim problems. So now we're going to go back to doing that. So please read along in the book. We're going back. Section 3.2, page 125, and then we're going to go forward. And so a bit of a review. We've been doing steady state. Which is really kind of statics, right? There's no accelerations. We have constant rates, constant velocities. It doesn't mean we have constant position, so it's not like statics, but it's equilibrium. And that's because we have zero accelerations both in linear and angular. And in fact, that's how we came up with the steady state equations of motion. Is we went to the full-blown nonlinear equations of motion and we made that happen. And then on top of that, we would say, okay, for rectilinear flight, P, Q, and R are 0. And then for a turning flight, Q is 0. And for a pull-up, P and R are 0. So we specialize different cases. And we needed these steady state forces and moments to plug in to the steady state equations of motion. So this is where we had our linear models. For CD, so CD FAX is minus CD Q bar S, and then we have the linear model for CD. This is all for steady state. Plus whatever stuff we have on the airplane, like we have flaps, you put those in here as well. And those are the matrices that we developed that are steady state forces and moments, longitudinal and lateral directional. And when we solved it for a turn or a pull-up or whatever, we would plug those models into the F's and the M's and the L's and the N's. So these are steady state equations. There's no differential equation at all. All of this stuff was algebraic. So now we're going to jump to dynamics. And the way we're doing that, remember, is we have small perturbations about the steady state flight conditions. And these are dynamic differential equations that we'll eventually solve using Laplace transforms. And again, remember the reason that we do the small perturbation stuff is that we can't solve the nonlinear equations using ordinary differential equation techniques. You have to integrate or do numerical methods. And so we linearized, but we still have differential equations. And we did that via the small perturbation analysis. Etc. And then for these equations, we need the stuff that's little FAX, because we added that to the steady state part. So the steady state forces are what we use for the steady state equations, and then these show up in the small perturbation equations. So we need linear models for these now. And it's going to take a couple lectures, maybe 3, to do this. It's not super exciting, but it introduces you to the terms that you need to know when we go to solve the equations. And we talk about some extra effects in detail that are important. Like, remember even when we solved the steady state equations, we included a pitching moment due to pitch rate. And we didn't really talk about where that came from, so we'll talk about that here. And we'll talk about rolling moment due to roll rate and things like that that are important for damping the aircraft motion. Because now we're talking about motion. All right, and we're going to specialize. There's a special case. We're not going to do all of the cases, but the case that the book does that we're going to focus on is symmetrical thrust. And it's going to be a cruise flight condition with 0 side slip. So really, we do this for the cruise case. Make sure I got it all. Yeah, symmetrical thrust. I mean, we could do non-symmetrical thrust. I was searching for the word there. Non-symmetrical thrust, but that's the case we're going to do as an example of how you do this. All of this could be applied to a pull-up or a turn or any other condition. You just have to use the right rates when you do that. So we have these small perturbation variables. So we got little u, little v, little w, little p, little q, little r, theta, psi, and phi, although these don't show up too much, especially because we're talking about cruise condition. But just like in steady state flight, we're going to define a small perturbation alpha and a small perturbation beta, because those are a better way to represent v and w in terms of the forces and moments, because we know how lift changes with alpha. It's more direct, and that's how our models typically are done. So we're going to define those. So I'm going to draw a picture, and it'll be obvious. It's just the trig on the geometry of the velocity vectors. But we want to get everything solid in our mind. So draw this picture with me. We're going to define alpha. And remember, this is not alpha 1. This is the small perturbation alpha, although along the way you'll see alpha 1 as well. So draw the x-axis, body fixed axis that way, and draw z down. And then draw the relative wind coming in like this. And we're doing this in stability axis. I need to add this to the list here. Which means W1 is 0. So the steady state flight condition has no side slip, so V is 0 and W is 0. So all we really have in that condition is the forward speed U1. So draw that vector. So that's the steady state flight condition. And in fact, this is the angle of attack of the airplane, right? Because here's the wing. I mean, we could imagine the wing being lined up with the x-axis here. And the wind's coming up. And again, there's no W. You maybe would think there'd be a W vector, but we're in the XS, ZS axis, and in fact, draw those in here. So put a little version here, put an XS here, and a ZS here. So in stability axis, all we have is U1. And now we add on the perturbations. So add a little perturbation on the end of this, U, because U1 gets perturbed by this amount U. And then W, which was 0, now has a small W component. And this is the perturbed velocity here. In the XZ plane. So forward flight, steady state, U1. We could have a forward gust and a vertical gust. So you just add those vectors tip to tail on. And then this angle here is the perturbation angle of attack alpha. Because that's what it is. It's the angle of the extra W compared to the adjacent. So tangent of the little perturbation alpha is W over U1 plus U. And the total velocity vector, V sub P, perturbed, is U1 plus little u, so that's that part, and that's in the I direction, and it's W in the J. And then we're going to draw a picture looking down on this so we can see V, but V is the side velocity added on. And that's J, not K. And as engineers, we're lazy but smart, right? I always say that. The important part is you're smart. You're not just lazy. And so we're going to look at this and say, well, some of this stuff is small. Can we make our job easier? So what's small here? W is small. But if we say W is 0, then we have no angle of attack, because W is what's creating the small perturbation angle of attack. How about U1, small or big? That's going to be pretty big. That's our flight speed. How about U, little u? Small. So we look at the denominator and we go, gosh, this could be like 200 feet per second. And this is going to be like maybe 0.1 small perturbation. And when we take the tangent of this, or the inverse tangent, we can say that this is pretty small. We don't just say it's small, we say it's small compared to this number it's being added to. And then how about this angle is small, right? Because W is small. So in fact, we can say the tangent of a small angle in radians is pretty much just the value of the angle. It works up to like about 2 or 3 degrees. Well, that's good enough. And so in fact, we can say that the tangent is approximately just the small perturbation. And that makes things a lot easier when we're going to do Laplace transforms, because the tangent, you can't take the Laplace of a tangent of a dynamic variable. But here we've got a nice linear relationship between alpha and W. So we'll use this all the time. Okay, so we're going to draw a top view, which for some odd reason I've got myself cornered into drawing below. But you guys can flip it in your head, right? So this is a side view. Now we're going to draw a top view. I'm going to try to get it centered right under here. So there's the CG. There's the X and the X axis, because we can't, looking down, we don't see the difference between that. Z is into the board, but now we can see the Y and the YS axis, which are both the same. And what we're seeing now is the full velocity vector. Try to draw it all the way out to this point here. There we go, it goes up to there, so that's V sub P. That's the total vector. And then we can see now the side component, velocity V. And in fact, this vector here is that XZ component, right? So we've resolved V sub P into VXZ and then added in the Y. So VXZ is this stuff all together. And then, of course, this is our small perturbation, beta. And again, we're lazy smart, so we're going to say what's small here. When we look at V sub P, we're talking magnitude here. So what's the magnitude of our perturbed velocity vector? It's the square root of u1 plus little u squared plus w squared plus little v squared. So we said little u is 0.1. Again, 0.1 compared to u1. We could pretty much say that that's small. And then we still got big O u1 sitting here squared. So 200 squared is 40,000, right? Did I do that right? Yeah. Squared is 40,000 compared to 0.1 squared, which is 0.01. We can pretty much knock that out, and W is on the same order. This is small. So as long as we got the U1 sitting here big, we can knock a whole bunch of other stuff out. And we can say that this is approximately equal to beta. Sine is the angle. So beta is approximately the side velocity over the forward velocity. And again, that means we can Laplace beta or V and not have to deal with derivatives inside this thing, at least for this part of the representation. Okay, just like the steady state forces and moments, we have to decide what depends on what. And we're going to split it up into longitudinal and lateral directional, just like before. So we've got U, V, and W, P, Q, and R, and then beta and alpha. So we're going to make the assumption that the longitudinal aerodynamic forces and moments are some function of U, W, or alpha, because they're connected, now we know that. Pitch rate, Q, W dot or alpha dot, and I'm going to have to explain that here in a minute. Elevator, and flap. Oh, and by the way, you go elevator. Well, we're defining, just like everything else, we have some steady state trim elevator, and then we add a small perturbation on there. So this would be like the airplane's trim flying along, and then the pilot pulls back on the stick very quickly and a small amount. That's a small perturbation on the elevator. So this is the steady state trim. This is some small delta E perturbation. So this is longitudinal, and those are the longitudinal variables. And we're making all kinds of assumptions here. We're saying that side slip beta doesn't affect any of these. Well, if beta is small and we're not stalled, then it won't. Yeah. Oh, flap, F. He considers the flap a perturbation on the zero flap condition. There, I'll make my F a little better. And then lateral directional. So we've got side force, rolling moment. Make sure you make it lowercase because that means a small perturbation. And these are functions of side velocity or beta, small perturbation, little p, little r, v dot or beta dot, because they're related, delta A and delta R. And again, these are perturbations on steady state rudder and steady state aileron. Now for most cruise flight, delta A1 is 0, right? And beta 1 is 0, and rudder, delta rudder is 0. But we still need to remember that when we solve for this, this is a perturbation on some steady state trim condition that we've already solved in chapter 4. So you can see why we did chapter 4 before we did this, because you have to. Your book has a chart where he creates a matrix that shows all this. So I'll point you to that real quick. So this is on page 125. No, it's not. 126. And you read this just like any chart. Here's FAX, here's the drag. It says the drag depends upon forward speed, vertical speed, which is really in terms of alpha, W dot, alpha dot, elevator, and flap. And he leaves out the lateral directional and the longitudinal. Pretty much by the time we're done with this chapter, you'll have this memorized anyway, especially since you know it might be a question on the test. I don't mean the chart, I mean the linear models that we're going to develop. So the next part, with what time we have left today, we're going to start on and probably finish just an outline of why each one of these terms is included. Some of them are real obvious, some take a little bit of thought. So I thought at this point I'd switch over to the notepad since sometimes it's clearer to do that. So here's our outline. And the first variable we're going to look at is a forward speed perturbation. So that's little u. So that's the first variable in our list. So the first question, we know alpha affects the forces in moments, so does this affect alpha? And we're talking about little alpha, the smaller perturbation. So what's the full-blown deal of alpha was W over U1 plus little u, right? And so you say, well, yeah, little u does affect alpha, but remember we made some approximations. So with that approximation, this forward speed perturbation really doesn't impact angle of attack very much. So why do we include it in the list? So there's two reasons, reason A and reason B. So V sub P, magnitude, was this. So does little u affect the velocity, the total magnitude? We can pretty much say this is small, and this is small, and inside the square, this is small, but if you remember, if we multiply that out, so let's knock these out, get rid of them. We've got the square root of u1 squared plus 2 u1 plus little u squared. You look at that and you go, well, we can knock out that. But this might be significant because although we have little u, we have big U1 multiplying by it. So in fact, that is the effect of A, is that the dynamic pressure, which is 1/2 rho V sub P squared, changes with little u. Let me get myself some more room. So you all see that, right? Dynamic pressure, even though u is a small change, could change with little u. So that's one reason why we include it. And the other reason is that because V sub P changes, then the Mach number changes as well. And this can be a big effect if you're flying close to the speed of sound, because small changes in the forward speed can change the shock wave pattern on the wing or the fuselage. So this is a Mach number effect. I always think for us AEs, it's kind of cool that WSU shockers includes shock, right? The first part of shock wave. In fact, there's a volleyball team associated with WSU called Shockwave. Okay, so U, that's the reason we include U. Okay, how about the second variable? So now we're talking about lateral speed perturbation V or beta. And this is pretty obvious because we've talked about how beta changes the yaw and the roll and all of that. So beta, the beta effect on like the rolling moment and the yawing moment and the side force is obvious. But how about the dynamic pressure or the Mach number, which are all related to V sub P? So to answer that question, we scroll back up and we look at our velocity here, and we see that when we square those small disturbances, either V or W, it's not going to change the dynamic pressure much. And it's not going to change the Mach number. So really, it's just this effect that we look at. Okay, the next thing is the vertical velocity W. What is that effect? Okay, I've got a vertical velocity perturbation. We're talking about W or alpha. And it's pretty much the same story as number 2. The alpha effect is obvious. I don't think there's an E in obviously, is there? This obviously changes the pitching moment and the force in the X and Z directions. But again, not so much on the Mach number and the dynamic pressure. Same reason, because W's over there, it gets squared. This is an H up here, so this is not so much, not so much. So the first one took a lot of explanation because U can change Mach number and dynamic pressure, but V and W, we talk about those all the time with regard to aircraft forces and moments and aerodynamics. Okay, we're going to look at P, Q, and R all together. So we're going to knock those out. So this is 4, 5, and 6. So we're talking about P, Q, and R. Perturbations. And this is obvious as well, because these cause changes in the airflow. And so they affect all the forces and moments. And in fact, that's the fundamental reason behind the alpha and the beta perturbations is alpha changes the airflow around the wing, beta changes the airflow around the vertical tail. And so changes in airflow, we know, changes the aerodynamics and changes the aerodynamic forces and moments. So I guess we should put an A on the bottom here. All right, so that was easy. And when we get into talking about these, I'll bring in the foam airplane and we'll spin it with like a roll rate, and we can see which parts of the airplane do what when it spins. Pardon? Well, when I say spin, I'm just going to take it with my hands and, okay, it's not spinning, it's turning. Yeah. That would be cool if we could put it into a steady state spin, huh? All right, so alpha dot and beta dot. So alpha dot or W dot, are rates of change of those. So the question is, why is that a big deal? I mean, alpha is alpha. It's at 10 degrees. Maybe it changes to 11 degrees. That's our perturbation. But why would how fast it changes from 10 to 11 degrees affect the forces and moments? Because that's what this says. How fast, d alpha by dt, that's how fast it changes. And we'll go into the details of this a bit later, but fundamentally, this is related to what's called the lag in downwash, or for beta, the sidewash. Model. So here's a wing, and because it's a finite wing, you get a wingtip vortex. When it's producing lift, that causes downwash. So you get downwash here. And we talk about that as a downwash angle epsilon. So the wing produces a wake that propagates backward through the air and eventually hits the tail. And we model that as a downwash angle. So the deal is that the downwash back here at a certain time t is caused by the downwash that was generated delta t seconds ago. Because it takes the velocity of the flow. The flow has to go backward. So we can calculate the distance from the wing to the tail and figure out how long it takes for the downwash to get from the wing to the tail. And if this is changing, then you get an alpha dot effect, because how fast alpha changes is going to tell you how long that change takes to get back here, and that's going to be the lag. So if alpha is constant, there is no lag, because alpha is just alpha and it stays at 10. But if we go from 10 to 11 in 1/1000th of a second, that change in the airflow around the wing takes a while to get back here, and that is going to be modeled as an alpha dot effect, because, and you don't see alpha dot anywhere in here, but this is because of our friend Taylor, who invented the Taylor series. You remember that you can model a variable at some time delta t relative to t as alpha at t plus d alpha by dt times delta t. And you get a bunch more terms that usually you neglect, as long as d alpha squared by dt squared is small. And so there's alpha dot. So it really is the lag in downwash, the change, or the delta t in the downwash. That lag we model as an alpha dot effect. So you can't immediately look at the airplane and go, oh yeah, there's alpha dot. But if you do a Taylor series on this lag, then you get that. And it's the same story with beta. And then it's the lag in the sidewash. So again, we'll go through this in more detail and derive these effects. But this is just an outline that we're doing right now. Considered a what? Oh, yeah, I lost track of my numbering, didn't I? Yes, that's actually 7 and 8. I think that's the end of our list. Oh, the control variables are obvious. We'll write those in a minute. But I want to ask this. What about if P, Q, and R are changing quickly? If P is changing rapidly, now I don't mean P is that the airplane is rolling fast, it's that the roll rate is accelerating fast, then that obviously changes the airflow over the wing, and that same lag effect will come into play. The lag of the change in the airflow about the wing, because it's accelerating in roll, and it takes a while to get to the horizontal tail. So we could say, hey, there's a P dot effect. Same deal with pitch, because if you pitch the wing rapidly, you can get changes in airflow. And the same thing for the R dot. So how about those effects? Legitimately, we should include these. For most flight, these are considered to be small. So when you say most flight and most airplanes, if you imagine a fighter aircraft flying at high speeds and they go into a real quick snap roll, that acceleration from level flight into that snap roll has high rates. And so if you're trying to model that, you would have to include some additional effects for these. But we're not going to include them because we don't want to. They're not on our list on the board. And they are small for most of the stuff we're doing. Okay, so that was 7 and 8, right? So now we're going to do 9, 10, 11, and 12, which are elevator perturbation, flap perturbation, aileron, and rudder perturbations. And these are easy and grouped together because they obviously change the airflow. Botch that up. And so that's going to change the aerodynamic forces and moments. So that's why they're included. I need an E, don't I? All right, last thing, and then we'll go home and sit by our fire if we have one. Because it's supposed to get down to like 39 tonight, I think. Is it tonight? Yeah, I think it is tonight. It's supposed to get pretty cold. Hope it warms up. I've got a high school football game to go to tomorrow night. Okay, promise, last thing. This will take 5 minutes. So here, as an example, I'm going to write out FAZ. So this is the lift. And we know the units on this thing, so we're going to be looking at units. This is force per unit area times area. So that gives force, which is good because that's force there, right? We want to get force out of this. What are the units? Wow. It is time to go home. Fortunately, I got this magic eraser. So what does that mean the units are on this? Well, we know that the coefficients are unitless, right? What are the units on alpha? Somebody say radians? Yeah, and that's unitless, right? It's dimensionless because a radian is an arc length over a radius, so it's unitless. Same thing for IH, same thing for delta E. So all of the variables in this linear expansion for steady state, this is steady state, are unitless. So now let's look at our small perturbation. So an example of our model for that, let's look at small perturbation FAZ. It's going to be a function of, and we're going to write our model out a little later, but it's a function of u, little alpha dot, q, delta E, and delta F. And we'll write it in terms of coefficients and multiply by q bar s, but I want to look at the units of the variables in here. So here u is feet per second. Alpha is in radians, so we're good there. But now here we've got radians per second, so that has units of 1 over seconds. Pitch rate is radians per second, ditto. Oh, this one's good, radians. But we've got these that are not unitless. They're not dimensionless. So we're going to fix that. We're going to do non-dimensional variables. And so we have to decide, well, what do we divide by to make it non-dimensional? And for velocities, the most obvious is to divide by the forward speed. So that makes it dimensionless. And how about v? Well, you divide by the forward speed. But hey, that's already beta. So that's nice. Our variable beta is actually a non-dimensional side velocity. And how about w? We'll non-dimensionalize that with respect to u1. But then we go, hey, for that one, that's just alpha. So alpha is a non-dimensional vertical velocity. And then it gets serious because we divide alpha dot by 2 u1 over c bar. Alpha is a longitudinal variable. C bar is a longitudinal dimension, characteristic dimension. Forward speed, does this get rid of the units? Convention. So what is it? Here we got feet per second divided by feet. So we get 1 over seconds and it becomes unitless. And so now you see where that weird combination came from when we modeled Q and R, because we do the same thing with pitch rate. We divide Q by 2 U1 over C bar. You flip the C bar up, and that's what we used to write is Q C bar over 2 U1. Dimensionless. Beta dot. So we divide beta dot by 2 U1 over C bar. And we go, wait a minute, C bar is not a lateral dimension. C bar is a longitudinal, so let's use B. Yeah, we use wingspan because that's more characteristic of stuff laterally directionally. And roll rate, same deal. And so now we have all non-dimensional. Dimensionless. I should have stuck with non-dimensional. Hey, I just discovered something. If I push this button on the pin, it turns into the eraser and I don't have to go select it. That's nice. That's where I want to stop. We've done a lot of just preliminary stuff that's not all exciting. Airplanes aren't flying around and moving. But this gives us all variables that are non-dimensional. And so and we'll see how when we derive, say, the vertical tail effect on this, how that U1 comes into play and helps us define those parameters much more easily, and they can be general for any flight speed, not a particular flight speed.